Hi everyone, I'm Yuxiang from HPST. Today I will present our work, the sum of the better and indexing approach to shared planning queries. This is a joint work with Yuxiang and Guang from Beihang University and Lei from HPST. This is the outline, and we'll start with the background. Our work focuses on route planning, which is important in many applications such as ride sharing, food delivery. For instance, in platforms like Didi and Uber, we may receive several ride-sharing requests. The platform needs to plan a route for each taxi to serve some requests, and the passengers may share the seat during the route. Similar problem also occurs in food delivery platform like Seamless. In all these applications, one of the fundamental challenges is how to plan routes shared among requests for the vehicles. Next, we will introduce a formal definition of this route planning problem. We first start with the basic concept. A vehicle is denoted by W, where W is current location and CW is the capacity. A vehicle satisfies the capacity constraint if the number of requests it takes is less than the capacity. The request is defined as R is an origin, a destination, a release time, a deadline, and a payment. The request satisfies the deadline constraint if the request is delivered at destination before the deadline. Another basic concept is the route. A route is a sequence of locations where the first location in this sequence is the current location of the vehicle, and the other locations are either origins or destinations of the request assigned to this vehicle. For example, the fig shows a route of vehicle W1 with a capacity of 3, which is marked by blue arrows. All these locations are in a Euclidean space, so we can derive the request R1 is delivered at time 8.4, which is earlier than the deadline. We say this route is feasible since it satisfies both deadline of request and capacity of the vehicle. Finally, we present the complete form definition of the shared route query problem. In this problem, we are given multiple vehicles and requests, and we aim to plan a route for each vehicle such that the total revenue can be maximized. Here, the total revenue equals to the total payments of the served requests, since some of the requests may be not able to be served in practice due to reasons such as short deadline. This problem has two constraints. The first one requires that each route is feasible. The second one requires that each planned route takes the shortest travel time. In other words, we do not want vehicles to waste time while earning the same amount of money. Here's a toy example. There are two vehicles here, and there are 4 requests, for example. The origin and destination of the first request R1 are marked by red dots, and here are the information of the other requests. The problem aims to find routing plans for these vehicles to serve 4 requests in order to maximize the total revenue. Here is an instance of the routes. Specifically, the blue arrows denote the route for vehicle W1, and the red arrows denote the route for vehicle W2. As shown in this figure, all requests are served, thus the total revenue of this solution is 18, which is optimal. Although an optimal solution can be easily found in a small instance, we prove it is NP-hard and APX-hard as long as the vehicle's capacity is no smaller than 2. The only special case, when all vehicles' capacity is 1, is polynomial time solvable with variety matching. Quite a lot of Zeng solutions are designed based on the idea of variety matching, which will be briefly introduced next. We'll start with this special case where a vehicle can serve only 1 request. Under this setting, we can construct a bipartite graph where left-hand vertices represent vehicles and right-hand vertices represent requests. So if a vehicle can serve any request, we create an edge between the corresponding left-hand vertex and right-hand vertex. Here, the edge weight denotes the revenue of this assignment. After constructing the bipartite graph, we can compute the maximum weighted bipartite matching to determine the assignments between vehicles and requests. Indeed, in this example, the optimal matching is R1 to W1 and R3 to W2. In recent years, this work extends this idea to a general setting, where requests are shared to be served together. Intuitively, the right-hand vertices now represent the groups of requests that can be shared. Again, we can compute the maximum weighted bipartite matching of this graph and derive the planned routes for 2 vehicles. In this example, we can observe that the request R3 is assigned to both vehicles based on the bipartite matching. As a result, the request R4 is not assigned to anyone, although W2 can actually serve it. By theoretically analyzing such situations, we prove the approximation ratio of such solutions is at least omega 1 over m, where m is the number of vehicles. For instance, when there are 1,000 vehicles, the effectiveness of such solution is at most 0.1% of the optimal result in the worst case, which is not acceptable. Moreover, constructing a graph consumes large space and computing the matching consumes high time cost. To address these limitations, we introduce our solution. The idea is simple. For each vehicle, we just assign to him or her the most profitable group of currently unassigned requests. Here, we can temporarily regard the most profitable group as the most profitable right-hand vertex in the bipartite graph. To elaborate on our idea, let's get back to the toy example. We first plan the route. For the first vehicle W1, currently no request has been assigned yet. Thus, the request group containing R1, R2, and R3 is the most profitable. Thus, we can assign this request to W1 and plan the routes as shown in the blue arrows. Next, we move to the next vehicle W2, and the only unassigned request is R4 now. Thus, we assign R4 to W2 and plan the route as shown in the red arrows. If there are more vehicles, we'll keep doing this until all the vehicles have been enumerated. Although this idea is very easy to understand, we formally prove that this idea leads to a constant approximation ratio, 0.5 without any assumption. Now, the remaining issue becomes the efficiency. Existing bipartite matching-based solution is inefficient, since it enumerates all combinations of requests. We design a new index called additive tree. Here's the basic idea. Intuitively, a group of 3 requests could be shared if groups of any 2 requests can be all solved by some vehicle. Inductively, a group of k requests could be shared if all groups of any k-1 requests can be solved by some vehicle. Based on this idea, we design an index like this. At the first level, we create n nodes to represent each single request. At the second level, we create the request group formed by 2 requests. Specifically, we create the child node by adding 1 request into the group of its parent node. How to do this efficiently? We can enumerate each sibling of this parent, which has only 1 different request from this parent. For instance, the leftmost child in this level can be viewed as the combination of this parent and this sibling. Similarly, we create other nodes. Each node also maintains the information like the profit of this node. The maximum profit is rooted subtree. To find the most profitable request group using this index, we use a branch and bound searching procedure in this tree. Moreover, we also present further optimizations to improve the effectiveness and efficiency. Due to time limitation, we refer readers to our paper for these technical details. Now, we present the evaluation. Our evaluation is conducted on 2 root datasets from Yuxiang and compared with 3 state-of-the-art solutions. Among these baselines, MWBM denotes the bipartite matching-based solution. In terms of effectiveness, our algorithms always have higher revenue than the baselines. For example, at least 17% higher revenue than the baselines. In terms of efficiency, our index can save over 4,000 times running time and nearly 80 times space usage. Finally, here's our conclusion. We propose an indexing-based solution to solve the shared route planning query problem. Our indexing-based approach not only has a constant approximation ratio, but also shows good scalability in real data sets. That's all for the presentation, and thanks for listening.